Hello, hello, hello. We are in lesson 15, session 2 today, and we're going to continue learning about functions. So if you could turn to page, what is this? 353. So page 353, you'll find this at the top. So page 353 in your book. Our goal for today is to develop an understanding of linear and nonlinear functions. So we started talking about functions last time. So what is a function? Well, maybe you recall that a function, and I'll bring us back to this page, a function is where every input has one output. So you input something into this equation or function and you'll get one result, one output. So you can recognize functions different ways. So let's just look at the two examples here with tables. If I input 1, I get 2. If I input 2, I get 4. 3 is 6. You can just kind of see it's multiplying the x by 2 to get to the y. So that's a function. Whereas this second example, we have 1 going to 2, and you also can input 1 and get 5. For that reason, it's not a function because that one input of 1 has 2 outputs. That would make a computer explode because it doesn't know which one to go to. If you input 1, what do you want the result to be? These are mapping diagrams. These are examples of mapping diagrams where it maps the input to the output. If you see here, 10 has one output, 20 has one output, 30 has one output, 40 has one output. This is a function. Whereas this one is not, because look at right here, 2 goes to 2 different outputs. You can input 2 and get 2 different results. That is not a function. And finally, if you look at a graph, we've very briefly talked about this on last time, but it's called the vertical line test. If you take a vertical line, let's say this is my vertical line. All right, if I take that vertical line and I can move that anywhere, and if I move this along a graph of a line, and if it crosses 2 points at the same time, it does not pass the vertical line test. I'm looking at this and it's never crossing 2 points of this line at the same time. So this right here is a function. It passes the vertical line test. Whoa, that's not at all what I meant to do. Anyway, this is a function. If I take my vertical line and I go across this one right here, it only ever passes 1 point on that blue line at a time. It passes the vertical line test. This is a function. If I take it past this circle one, and I can stop pretty quickly because boom, it's crossing 2 points at the same time, here and here. That means if you input that, whatever, -1.5, you'll get 2 outputs. You can get a negative or a positive, and that is not a function because it does not pass the vertical line test. So what I want to talk about today then is linear functions, which is nothing new because we did a whole unit on linear equations. So let's look at the examples on page 353. Number 1, it says functions can be classified as linear or nonlinear. Look at a linear function. So we've talked about what the word linear means. It has that root word line in it. So a linear function is something that graphs a line. Okay, it has a constant rate of change, as we used in the last unit. So let's look at this example of birdhouses. It says input the number of birdhouses Amy paints with 0.5 pints of paint each, and the output is the total number of pints needed. So if you have one birdhouse, you need 0.5 pints. Now if I look on a graph, one birdhouse is right here, half of a pint would be right there-ish. There's a point. So 2 birdhouses would need twice as much, that'd be 1 pint. 3 birdhouses, you need another half a pint. 4 birdhouses, you need another half a pint, and so on. You're adding a half a pint for every birdhouse, and so 2 is right on the 1 pint, 1.5 for 3. Sorry if my dots aren't perfect. 4 is 2 pints, 2.5 for 5, and so on. And you can see it with 0 pints, obviously it's going to be 0. But if I graph that, look at that. If I connect the dots, what does it look like? If my dots are perfect, it's a straight line. Now it's a function because it passes the vertical line test, but it's a straight line, so that is linear. So why do you think it's classified as a linear function? Well, we've kind of answered the question. Graphs a line. And we've actually talked about linear functions. Anytime you have a linear function, it's going to be in the form y equals mx plus b. So you can figure out the rise of a run up 1 and over 2 will be my slope. And my y-intercept is 0 because it goes to the 0. So there's my equation of this one as well. Okay, that's the function. Now, number 2 says complete the table and graph for this nonlinear function. So input x is an integer, output is the square of an integer, x. That's like x squared. So if I'm going to do x squared, that means I'm multiplying it by itself. So for -2, it's -2 times -2. And that's going to give me a +4. -1 is -1 times -1. Negative times a negative, again, is a positive, so this is +1. 0 times 0 is 0. 1 times 1 is 1. 2 times 2 is 4. So there's some repeats in the outputs, but that's okay, because every input still goes to one output. So it is a function. Let's see what it looks like on the graph. -2, 4. I go over 2 and up 4. That's where my first point is. -1 and 1. 0, 0. Oh, sorry. 0, 0. Then I have 1, 1, and 2, 4. So if I connect the dots, it kind of will round like this and make a sort of U shape. It is a function, but it is nonlinear because it does not graph a straight line. So it is nonlinear. It is a curve. So if you need to make a graph of a function, you can always find input and output values. You can pick your inputs as, and these are good common ones to use, just -2 all the way up to 2. And that'll give you a good gauge as to what the function looks like if you find the output values. So let's turn the page and go to page 353 and look at a couple of these examples. Now, number 3 says, many functions can be represented by equations that show how to calculate the output y for the input. And one great way to do that is to make a table of values if you don't know if it's going to be linear or nonlinear. Now, obviously, some of them you might know that they're linear just from what we've learned about linear functions already, or linear equations. Like, for instance, this one in the blue here is y equals 2x minus 1. Well, the y-intercept is -1. The slope is 2 over 1. So I can graph it starting at -1, go up 2 and over 1, up 2 and over 1, and I got a line right there. So that's linear. I know that because it's the form that it's in. If I jump all the way to this last one too, I'll put this one in red. Same idea. It's in y equals a number times x. Remember, you can put a 1 in front of it if there's nothing there. So my y-intercept, there's nothing there, so it goes at the 0, the origin. And the slope is -1 or -1 over 1. So I go down 1 and over 1, down 1 and over 1, and I can draw my line through there. So that's linear as well. We know those are in forms that we've already worked with that graph a line. Whereas this one in the middle, we have not worked with an example like this before. So if we don't know how to graph it from other ways, we can always make a table of values. So I'm going to make a table. It's called a t-chart, x and y, and I'm going to pick at least 3 values. The more the better. But let's just pick 3 numbers like we'll go -2, we'll go 0, and we'll go +2. So a negative, and a 0, and a positive. And we plug them in. Let's just plug in -2. So negative of a -2 squared is what we're plugging in for this x. Because you got to plug it in, plug it in, plug it in. Plug it in right there. So negative 2 squared is 4, and then the negative of that is negative 4. Okay. Now, if I try that with 0, I would have a negative of 0 squared, and 0 squared is 0, and a negative of 0 is 0, so I get 0. Now, if I try that with a positive 2, I would have negative of a positive 2 squared. Positive 2 squared is 4, and a negative of that is still negative 4. So I've got 3 points here that I can graph and just to see what it looks like. So in green, negative 2, negative 4, negative 2 down, and then down 4, there's a point. 0, 0 is at the origin, and then 2 and negative 4 is down here. So this is actually kind of like that last example. It looks like a V, but if you fill in more examples, it'll make this upside down U. And anytime you see a squared, now we can assume that it's going to be nonlinear because we've already done 2 examples now of those where it's not going to graph a line. So this is nonlinear. All right. B says, explain how you know that the equations of the form y equals mx plus b always represent a linear function. Well, we've learned that it's got a constant rate of change or slope. Constant slope. Never wavers. It's always going up or down by the same amount. So just to finish it up, it says number 4, you want to determine whether a function is linear. How can making a graph or writing an equation help? Well, you can see it on a graph, or you can look at equation forms. And then there's one example at the bottom. I'd like you to try this one on your own. It says, does the rule describe a linear function? Use a model to explain. And either we'll go through this in class or I'll have you check this with me. Okay? So if your input is any number and your output is 6 more than 5 times that number, give some examples or in a table or a graph, or make an equation if you can. See if you can explain whether that's linear or not. That's it for today on understanding linear and nonlinear functions. Have a great day.